Okay. First, I would like to thank the organizer and the committee for giving me this opportunity to attend this high-level conference. Today, I give a talk about two-dimensional spin-orbit coupling in ultra-cold Fermi gas. My group in the State K Laboratory of Quantum Optics and Quantum Optics Devices in Shanxi University. Here, I will present to our group recent work. First is 2D spin-orbit coupling, then go to the topological band gap opening for 2D spin-orbit coupling. Spin-orbit coupling is a hot topic in the field of ultra-cold atoms. 1D spin-orbit coupling in the boson and Fermi gas have been successfully demonstrated in experiment, and some exotic effects have been studied. 1D spin-orbit coupling, this Hamiltonian can be expressed as the matrix or the operators. This term, momentum, the product momentum and the spin operator represent the spin-orbit coupling term. This two-photon Raman detuning represents the effective horizontal Zeeman field, which will tilt the dispersion in the momentum space. Raman coupling strength represents the effective vertical Zeeman field, which will open the gap of this dispersion. Rush-bar or dress-hole coupling are the typical 2D spin-orbit coupling, which is a non-abelian spin-orbit coupling, and orangely present for 2D free electrons in presence of the uniform perpendicular electric field. Rush band dress-hole spin-orbit coupling have many novel features, such as two spin-dressed energy band contact only at a Dirac point and intersect linear or in all directions here around the Dirac point, and a continuous set of a minimum along a circle in one of energy band in here. So this system can be used to explore interesting topological and other exotic superfluid. Here, we mainly discuss the system with continuous travel potential. In parallel, cold atoms in the optical lattice with the gauge potential also have richer physics. Recently, USTC group in China realized the topological band by the optical Raman lattice scheme. Here, he used the Raman laser to generate optical lattice. Now I go to our work, experimental realization of 2D spin-orbit coupling in ultra-cold Fermi gas. Many theoretical schemes have been proposed to generate 2D spin-orbit coupling. The scheme of generating non-abelian gauge potential have been proposed very earlier by the laser atom interaction. In this scheme, it suggests to use the 3 Raman laser couple 3 ground states in tripod energy configuration. this tripod energy leads to degenerate dark state. So non-abelian gauge potential will become the 2x2 matrix in this pseudo-spin space of two degenerate dark states. Lately, this scheme was further developed by this work. When three lasers couple this tripod energy level, it will lead to degenerate dark state and two bright state. Here, the laser detuning is very far, is very large to suppress the spontaneous emission that hit atoms. We can see this two degenerate dark state is well separate in energy from the two bright states. We can see one of the bright state is separate in energy from the two degenerate dark state with one photon detuning dirt. Another bright state is separate in energy with omega square divided the dirt. Thus, we can project Hamiltonian into the subspace of the degenerate dark state. We can obtain the Rashba address Hall spin-orbit coupling by the one-order approximation. However, this scheme has a drawback because the degenerate dark states are not the lowest energy band of the dressed state. In this case, atom will decay out of the dark state due to the collision and other relaxation process. In order to solve this problem, a blue detuning laser is used to make sure this lowest bright state is far separate from the two degenerate states. We can see this energy separation with dirt, so it's very large. Thus, we can regard two degenerate dark state as the ground state of the systems. In our experiment, we employ the tripod configuration and large one photon detuning. How to generate this tripod configuration? We first consider to choose the three ground Zeeman states in the same hyperfine state. Here we encounter problems. The ground state 3 and 1, there is no Raman coupling. When the Raman laser detuning is larger than the hyperfine splitting of the excited state. In this case, Raman coupling for the hyperfine Zeeman state cannot couple the state with the angular momentum difference larger than 1 unit. In other words, only outside one electric spin can be filled when the Raman laser detuning larger than hyperfine splitting of excited state. In order to solve this problem, we choose another ground state in the different hyperfine state. Thus, this energy level can form the triport energy level. Here, a gauge transformation can eliminate the laser phase. So all the three Raman coupling becomes reals. This special laser relative phase should be 0 or pi. Our Z scheme is not sensitive. The relative is laser phase, and the sophisticated and challenging laser phase locking are no longer necessary. The ground hyperfine splitting for potassium-40 is about 1.2 gigahertz. Thus, we can use AM to generate 3 Raman lasers from a single frequency test-alpha laser. 2 Raman lasers propagate along these y directions with vertical and the horizontal linear polarization. Another Raman laser along x direction with the linear polarization along in the horizontal direction. We first resolve this Hamiltonian to obtain the energy band structure by the 2 lemmas. First lemma is 3 by 3 matrix has 2 degenerate dark states. The off-diagonal term is same as this our original Hamiltonian. However, this diagonal term is a special selection which depends on the Raman coupling space. We can see there are 2 degenerate dark eigenstate with 0 eigenenergy. The third eigenstate has the energy with this form. We can see this sign depends on this product 3 Raman coupling. For the positive or the negative 3 Raman coupling strength, the third eigenstate is ground or excited state respectively compared to degenerate dark state. Then we can let the diagonal of the Hamiltonian equal to the that of the matrix. We can determine the position of a Dirac point in the momentum space. Projecting the Hamiltonian onto the subspace of a degenerate dark state, we can obtain this Dresselhaus spin-off coupling with 1 order approximation. In our scheme, the Dirac point can move in the momentum space. So this Hamiltonian can be expressed as this form. So Dirac point is protected by the PT symmetry, which is recognized by recent work. As our discussion, all the Raman coupling strength is real. However, we can control this product of 3 Raman coupling, and we can change the Dirac point emerge to higher or lower energy band. When the wavelength of Raman lasers is at the blue detuning D2 or red detuning D1, the product of 3 Raman coupling is positive. So Dirac point will appear at the 2 higher energy band. When Raman laser is between D1 and D2, the product 3 Raman coupling is negative. So Dirac point will appear at a lower energy band. Here I emphasize in ultra-cold atom systems, we need the atom populate the lowest band. If in this higher band, we'll have the collision will decay out. In our experiment, we use the spin injection spectroscopy to probe the spin and momentum resolved band energy structure. We first prepare atoms in the single spin state as the initial state in here. Final state is a 2D spin orbit coupling. Then we apply the radio frequency pulse to drive initial state to the final state. At last, we take a time flight with the Stern-Geller effect. We take absorption images as a function of the frequency of alpha phase. So, we can get this energy band structure. The spin injection spectroscopy have been used to study 1D spin orbit coupling Fermi gas by the MIT group. This is our experiment result. When set the wavelength of the Raman lasers, blue detuning D2 or the red detuning D1, we can see this Dirac point appear at this higher energy band. When wavelength at the 768 nanometers, which is between the D1 and the D2 line, we can see the Dirac two energy band attack at this Dirac point. The Dirac point is created in our scheme is very robust. In this sense, that Dirac point can move in the momentum space when change the experiment parameters. But we cannot open the gap of Dirac point. For example, we change the two-photon Raman detuning, we can see Dirac point will move in the momentum space. We also measure the energy of Dirac point and the energy separation from this higher energy band as a function of Raman coupling strength. Now I go to the open and control the gap at the Dirac point by generating effective perpendicular Zeeman field. Because this is very important in the future, we study the topological superfluid. We must can exactly control this gap. First, let us see the previous scheme to generate this effective perpendicular Zeeman field. In this scheme, they use the three laser couple these three ground state like our experimental schemes. Two extra laser is used to couple ground state, the 1 and 3 state, and the two extra laser is with a different frequency compared to the original Raman lasers. Moreover, two extra lasers propagate along the original Raman lasers, Raman lasers 3 and 1. Thus, this extra Raman coupling appear in this Hamiltonian. If this extra Raman coupling becomes complex, it means the effective perpendicular Zeeman field is generated, which can open the gap at the Dirac point. How to generate this complex Raman coupling, we must control the actual laser's phase compared to this original Raman laser's phase. So this scheme needs two actual lasers with different frequencies and must control the relative laser phase. It is difficult to realize in the experiment. In our experiment, we control this polarization of Raman lasers to generate this effective perpendicular Zeeman field. So our scheme is easier to realize in experiment. Let us, I emphasize these schemes. Yeah, these schemes this is a frequency non-degenerate, and polarization is degenerate. In our scheme is frequency degenerate, however, polarization non-degenerate, so it's easier to realize. That's for our experiment setup. This 3 Raman laser couple the 3 ground states, same as the previous schemes. Here, we must know the polarization. This Raman laser 1 is vertical, horizontal, laser 2 is horizontal, this horizontal. Raman coupling depends on this selection rules. Then we add the new polarization in this Raman 1 in the horizontal, and the vertical polarization in the for the Raman 2. Thus, we can generate the actual Raman coupling. How do we generate this complex Raman coupling? So we need to control this relative phase. This requires the polarization is horizontal and vertical superposition, superpose the linear polarization along the 45 degree. However, for Raman laser 1, it requires this vertical horizontal superpose the circular polarization. So we can generate this effective perpendicular Zeeman field. Okay, we know this scheme. Our experiment result is simple. We first consider the two different cases. Cases is we rotated Raman 1 and 2. The polarization keep the linear, but keep the orthogonal. So all the Raman coupling keep the real, so we cannot open the gap at the direct point. For the case 2, we change the Raman laser is a linear polarization. We rotate from horizontal to the vertical. Then Raman laser 1 is a vertical, circular, and horizontal. So this Raman coupling becomes complex. We can open the gap at the direct point. We measure this Raman coupling by the Rabi oscillation. We can see this Raman coupling 1 and 3 and 2, 3 is changed as a cosine theta function. For the omega 1 and 2, this for the case 1 is keep unchanged. This one is changed as this function. So we can see when case 1, we cannot open the gap. For the case 2, we can open the gap. We also measure the gap opening as a function of the rotation angle of polarization. Okay, in conclusion, we hope to further study 2D spin orbit coupling with flashback resonance. Also, we hope to extend our scheme to the 3-dimension spin orbit coupling with ending the extra lasers. At last, I would like to thank my group member. At the same time, I would like to thank the happy cooperation in theory with Qizhou and Travis Zhang for this 2D spin orbit coupling. We also have the cooperation in theory with Hui Zhai, Pen Zhang, Shizhong Zhang, Wu Hui, Xia Jieliu, Han Pu for the previous work. Thank you for your attention.
Okay, thank you. So due to the time limit, we'll have a very short questions.
This is a very wonderful work. So may I ask you, what's the mechanism in your case can generate the Dirac point and also open the Dirac point compared to the honeycomb lattice? Because the honeycomb lattice is very typical to generate the Dirac point. This is based on, I think, the geometry structure, the bandwidth. But in your case, there is no lattice. You use a 3 laser beam. Why it can generate a Dirac point in the energy?
In our case, in the continuous trap potential, how to generate this is easy to understand. Let's see this picture. We use the 3 ground state. As we know, 1D Raman coupling, this opens this gap between these two. If we have a circular Raman coupling, the Raman coupling between the two states, these two states is 2 states. So when we add this Raman coupling, you can change this dispersion. So it becomes this round. So we can see this Dirac point between the 2 energy bands. This also like this 3 lasers to generate honeycomb lattice. Use the 3 lasers. You can see we can generate the triangle optical lattice for the red detuning or the blue detuning. You can generate honeycomb detuning. This is in the real space. In our case, it's Raman coupling. You can generate this shape in the momentum space.
Okay, thank you.
Okay, so let's thanks again. The next speaker is Professor Jean-Michel Raymond from UPMC Paris.